Hello and welcome to section 3.9 on antiderivatives. We have calculated the derivative of many functions. In this section, and the general theme of the remainder of this course, we attempt to reverse this calculation. That is, for a given function f, are there functions whose derivative is f? Graphically, when the derivative of a function is given, we are able to sketch an approximation of the original function. The problem is, having information on the instantaneous rate of change does not give information on y values for a function. For example, knowing that a car is traveling at 40 miles per hour doesn't help determine its position on the highway. We analyze this graph with the knowledge of Chapter 3 at our disposal. We see that the roots of the derivative at x equals 2 and x equals 3 are where the function has a horizontal tangent line. These roots divide the domain into intervals on which f is increasing or decreasing. As the derivative is positive between 2 and 3, the function is increasing on that interval. As the derivative is negative between 0 and 2, and then again after 3, the function is decreasing on these intervals. We can sketch the function f of x with this information, but we do not know where to pin the graph of the function. That is, we do not know the y values of any point on the graph. As this is a sketch, and we cannot find the y values, we'll just assume that the function begins at the origin. Then the function decreases at a quickening pace until x equals 1. And then the decreasing slows until the function has a horizontal tangent line at x equals 2. Then the function increases from 2 to 3, and hits a horizontal tangent line at x equals 3. And then the function decreases, but at a very slow rate. Eventually the function is barely decreasing and approaching a zero slope. Keep in mind that this is only a sketch, and one in which we are not sure of the actual y values. I have graphed 3 possible f's, but the actual function has the possibility to be pinned at an infinite number of points. We now move from a graphical to a more algebraic analysis of antiderivatives. A function big F is called an antiderivative of little f on an interval I, if the derivative of big F is equal to little f for all x in the interval. Take for example sine x is big F and cosine x is little f. The derivative of sine is cosine, so sine of x is an antiderivative of cosine x. In section 3.2, the mean value theorem was used to show that two functions with equal derivatives were the same up to a constant. This leads us to the definition of a general antiderivative. Once you find an antiderivative, big F for little f, then every antiderivative will be of the form big F plus c, where c is any constant. Now because the derivative of sine is cosine, every antiderivative of cosine has the form sine x plus c. We now will find the general antiderivative for the functions which serve as building blocks. We just calculated that the general antiderivative for cosine is sine x plus c. For most trig functions, finding an antiderivative will prove difficult. In fact, we won't be able to find an antiderivative for secant until the second semester of calculus. But we can reverse our standard derivatives of tangent, cotangent, secant, and cosecant to recognize them as antiderivatives of their derivatives. The first two functions on our list are not as simple to calculate as the bottom of the list, but they are the most useful. The derivative of cosine is negative sine, so the derivative of negative cosine is sine. Therefore, the general antiderivative of sine of x is negative cosine of x plus c. The derivative of x to the n plus 1, using the power rule, is n plus 1 times x to the n. If we assume that n is not equal to negative 1, then n plus 1 is not 0, which means that we can divide by it. Therefore, we can calculate the derivative of 1 over n plus 1 times x to the n plus 1, and find that it's x to the n. So we can reverse the power rule for the function x to the n when n is not equal to negative 1. The general antiderivative of x to the n when n is not equal to negative 1 is x to the n plus 1 divided by n plus 1 plus c. Since the derivative of a sum is the sum of the derivatives, the antiderivative of a sum is the sum of the antiderivatives. Similarly, the antiderivative of a constant multiple is the constant multiple of the antiderivative. Therefore, the general antiderivative of the function 4 cosine x plus 3x squared can be found by ignoring the constants, taking the antiderivative of cosine, which is sine, and the antiderivative of x squared, which is 1/3 x cubed. We find that the general antiderivative is 4 sine x plus x cubed plus c. Be careful with antiderivatives. It is not only a matter of applying a formula to calculate one. In fact, there is not a product rule nor a quotient rule for antiderivatives. Finding an antiderivative is more of an art than calculating a derivative. Take for instance the function 1/x squared and 1/x squared plus 1. As 1/x squared is x to the negative 2, and negative 2 is not negative 1, we know how to calculate the general antiderivative. We're just reversing the power rule. While the general antiderivative of 1/x squared plus 1 is the arctangent of x plus c. But don't worry, our antiderivatives won't become too complicated until the second semester of calculus. Suppose a ball is dropped with an initial velocity of 0 meters per second from a building which is 100 meters tall. Imagine wind resistance is irrelevant. Find the function representing the height of the ball with respect to time. We assume that the only force acting on the ball is gravity, which accelerates the ball at negative 9.8 meters per second squared. Since the derivative of velocity is acceleration, the antiderivative of acceleration is velocity. Reversing the power rule for derivatives, we find that the velocity of the ball is negative 9.8 t plus c for some constant c. In the problem, we were told that the initial velocity, times 0, was 0 meters per second. So 0 is equal to v of 0, which is equal to negative 9.8 times 0 plus c, or just c. So the constant c is 0. The derivative of height is velocity, so the antiderivative of velocity is height. We calculate the general antiderivative of the velocity using the power rule in reverse. And in the problem, we're told that the initial height of the ball at t equals 0 is 100 meters, which tells us that c is 100, and we've calculated the height of the ball. We now have the word antiderivative to describe the reversal of differentiation. We are able to calculate an antiderivative only for a limited number of functions. In chapters 4 and 5, we will find a number of uses for antiderivatives.